Hello, this is physical chemistry. We will finish up this section with introduction of operators, the uncertainty principle, the postulates of quantum mechanics, and then we will move on to the quantum theory of motion, structure and spectroscopy, molecular structures, molecular symmetry, and so on and so forth. So let's dive into this. We are going to begin with a brief review and then go on to actual operators. So as a review, let's revisit Max Born interpretation of wave function. So basically, what was Max Born's contribution? He basically took the wave function and applied it to a determining a location or trying to elicit information about a particle. As such, the Born interpretation tells us as much as we can know about the location of a particle. But in the grand scheme of quantum theory, the question is, how can we extract some additional dynamic information about a particle? And that's what we're going to be talking about today. So as such, we know that the Max Born interpretation can give us the maximum information that we can obtain about the location of a particle. But what about some additional information? So for that, we need to do some elaborate mathematical transformations. And to do that, we introduce the operators. And we do this to be able to come up with a systemic way of obtaining information about the wave function. So with operators, we can rewrite the Schrodinger's equation in this particular form. So this is an operator form of the Schrodinger's equation. And if we go a step further and write this for a one-dimensional system, this takes the form of Hamilton operator. Okay, but let's first talk about what is an operator. Okay, an operator is basically a mathematical operation that is conducted on a particular function. In this case, the operator is functioning on our function p. So, and furthermore, in this case, all this operator does, basically, it takes the second derivative and multiplies that by minus h squared over 2m. Okay, and if you remember from our initial introduction of the Schrodinger's equation, Schrodinger also has two parts, right? The kinetic and potential, and this is the potential part. Therefore, we can, to some extent, safely assume that this right here is representative of the kinetic energy part. Now, let's just back up a little bit and talk just a few words about the Hamilton. William Hamilton was a 19th century mathematician. He originally described his work, or did his work, in the realms of classical mechanics, but it turns out that his math is very well applicable to quantum mechanics also. So it is being widely used as a way to correlate the total energy of the system, which is, again, the sum of the kinetic and the potential energy. The next concept to be introduced is the eigenvalue equations. What are these? Well, basically, if we write here the the operation form of operator form of the Schrodinger's equation, which on a previous slide looks like this. This basically translates to an operator, the function, which then equals to a constant factor multiplied by the same function. Okay? Interesting. So this can be rewritten in a different form, which is its eigenvalue equivalent. So eigenvalue equation, which is in which we have operator denoted as big omega, uppercase omega, and the constant is denoted by a lowercase omega. Now let's change the terminology and write it in the form of eigenvalue equation. So we have our operator, as we denoted in this case to be an omega. The eigenfunction, our function is the phi. We have the eigenvalue, which is the small omega, and our function, same function again. So we can translate to the operator form of Schrodinger's equation, which is, as you remember, h hat omega equals e omega. Now, so the eigenfunction of the equation, this equation right here, is the wave function that corresponds to the energy E. Okay, now look at this, listen to this closely and follow it because it makes sense. Just don't get too lost in the terminology. When we say solve for solving the Schrodinger's equation, we can say it equally in an equally valid way by saying it, find the eigenvalues and eigenfunction of an Hamiltonian operator for that system. Think about it. Solving the Schrodinger's equation, it's finding the eigenvalue and eigenfunction of the Hamiltonian operator, right? So, well, let's do an example and see what we get. Now, as an example, let's do this simple operation and show that the e to ax is an eigenfunction of the operator d dx, and find the corresponding value. And furthermore, let's show that the e ax squared is not an eigenfunction for d dx. So let's put everything together. Our eigenfunction, which is the omega, is d over dx, right? And our phi is e to the ax, right? So our omega phi is d dx of e to the ax. d dx of e to the ax. That, in turn, then going back to the basic integration and differentiation, this equals to a times e to the ax, right? And this you can clearly see is alpha or A times our initial function phi. So we can safely say that our EAX is the eigenfunction of ddx. And therefore our phi is e to the ax. Now let's look at the other example. Now in the second scenario, in which we need to show that e to the ax squared is not an eigenfunction of ddx. Same logic, same thing happens here. We have our omega phi, which should equal to d dx times e to the ax squared, which of course in turn equals to 2ax times e to the ax squared, which then equals to 2ax, and this is our function here, times phi. Therefore, this is not an eigenfunction, because even though the same phi occurs, right? It's not. It's multiplied by a variable function, 2ax. It's not constant. And even if let's say we rewrite this in a constant form, 2a times x phi, our constant is by a factor of 2 different. So we can clearly say that this is not an eigenfunction of ddx. Now, here is a question, and a problem for you to solve at home. Let's say a function of cosine ax. Would this be an eigenfunction of d dx or d squared dx squared? Please write it out and send it to me as the assignment for this lecture. All right, that's that. Let's move forward. The pattern in eigenvalue equations is of utmost importance. The pattern that we see here, the energy operator times phi, energy times phi, we can more generally write it out, and this will hold true, in which we can write it as operator corresponding to the observable times phi, which equals value of the observable times phi. And that observable could be, well, any property of or measurable property of the system, such as momentum, dipole moment, and whatnot. And if we look at it this way, then the symbol omega can be then interpreted as an operator. It can be look out as an operator. For example, that could be an Hamiltonian operator corresponding to anything, energy, for example, anything observable, and therefore also the little omega would be the eigenvalue of the whatever observable of this operator is. For example, if we're talking about energy, then this would be energy E, right? So if we know both the wave function phi or phi, the operator omega, that corresponds to the observable of interest, and we would, let's say, energy, right? So we can predict the outcome of observable property of omega, for example, the energy, by picking out the factors of little omega in a atom value equation, which we talked about, which is this, right? We know this, we can determine it if we know that. So let's look at what this actually looks like and how we can apply it. Now let's look at a basic postulate of quantum mechanics. Let's say if we have observables that we already have denoted as omega, which are represented by an operators, and they are built from position and momentum operators, and in this case this would be the position, this would be the momentum operator, and we know this is the momentum operator, right? So the operator for location along the x-axis is basically the multiplication of the wave function by x. That's the basic postulate. And for the operator for linear momentum parallel to the x-axis is proportional to taking the derivative of the wave function with respect to x, right here. So let's try an example and see what it looks like. So here is an example. What is the linear momentum of a free particle described by a wave function, this wave function right here, with in case when b is 0 and second case when a is 0. So what do? We basically operate on our phi, which with an operator that corresponds obviously with the linear momentum. We're looking at the linear momentum, and then we look at the results. If the results are if the result is the original wave function multiplied by some constant, then the constant is identified with the value of the observable, the atom value. Okay, so let's look at the scenario in which b is 0. Okay, so what happens here? Our substitutions look like this, right? And it's fairly straightforward. It's just where we're plugging it from the previous equation, and then dx, right, times our wave function, which in turn equals to over I times a. Now this part right here is 0, so it's a d e to the I kx divided by dx, right? No mystery there. This in turn equals to h over I a times I k e to the ikx power. And this is where it gets interesting. This I and this I obviously cancel each other out, and we get k h, and we get our omega, right? So this is our atom value. Therefore, our px is positive kh. Now, if we do the same thing with setting our a 0, then we find that our atom value is minus kh. Therefore, if a is 0, then you can do the calculation yourself. Then px equals minus kh. So let's say we want to elicit the operator for potential energy, or let's say it has a form of this form right here, Vx equals kf x squared over 2. Now I'm going to keep this kf here as it's a constant, but when we start talking about the vibrations of atoms and molecules, this term here will be of interest, of importance. So going back to the previously explained correlation, in which we had we described the specifications of operators, we can then say that our operator for potential energy is, well, this, right? Now this is just basically plug and play from our previous described relationship. And now, taking in consideration the relationship between kinetic energy and linear momentum, in which, as you may remember, the kinetic energy is proportional to the x squared divided by 2m, basically. But if you do not remember this, please do not go into your mechanics physics book to elicit this, because what it basically boils down to, and what is important for this particular course, is that our operator for the kinetic energy is basically this right here, the 1/2. We have the 2m here, right? M. And we have the p. So, let's see, I made a mistake. It's a p squared. And p squared, if you remember, was the I times d dx, right? Just go back and look at it. So the operator becomes I d dx, and this is just plug and play, which in turn results in h squared divided by 2m, minus, times d squared times dx squared. Okay, so this brings us to the Hamiltonian operator, which basically is, we talked about this already, the Hamiltonian operator is the sum of kinetic and potential energies, right? Therefore, now watch this, this is quite fascinating. um, our Hamiltonian operator equals to h squared divided by 2m times d squared dx squared plus vx. So all of this basically comes down to the Hamiltonian operator, and that's what you need to know, because beyond the basic introduction, this is the foundational equation, shall we say, that we will use in characterizing the systems from this point on. So now, knowing the Hamiltonian operator, and in here looking at the kinetic energy operator, which is this right here, right? We can make some really interesting observations. Well, first of all, from the math, we remember that the second derivative of a function is a measure of its curvature, right? The larger the second derivative is, the sharper the curvature, right? So here we have two scenarios here. So if we have, this is our wave function. If we have a sharp curved wave function, it associates with high kinetic energy. And one with a lower curvature associates with lower kinetic energy. Now this is interesting because it's consistent with de Broglie's relationship. And if you do not remember de Broglie, please go back and revisit. But in general, de Broglie predicts that the short wavelength, when it predicts a short wavelength when the linear momentum is high. Short wavelength, linear momentum is high, high energy. But this simply expands to waves that do not spread through space. Okay, so this is a more generalized case. So by just looking at this, looking at each term, the kinetic and potential energy contributors to the Hamiltonian operator, we can quickly say that for this particular wave function, we have its contributing factor being kinetic or potential in nature. So if we have a narrow spike, a large second derivative, then our overall potential energy is low, our kinetic is high, and vice versa. So, and then a little bit more general, if we're talking about a particle, if we have a high average curvature of the wave function, then we can clearly state that our particle has high kinetic energy. So this correlation between the wave function curvature and the energy becomes very important, because if we need to know the wave function of a particle that has a total energy that, let's say in this axis, changes. If the potential energy drops here, the kinetic energy has to go up, right? If the total energy is the same, then we see a wave function, actually the second derivative becoming greater. And then we can assess about the potential energy or the contribution of the kinetic energy further on, in which if we have the curvature of the wave function dropping, we can say that that region actually contributes less to the kinetic energy, right? So we can clearly define a region in the wave function of a particle that contributes the greatest to its kinetic energy. Therefore, this would be the region in which the wavelength would be the shortest. Short wavelength, high energy. So here is another way to illustrate this. We have a simple relationship between the total energy on the bottom, delineated with this line here, and the wave function. And you can see that total energy obviously does not change, but as we go further in x, as the x gets larger, our potential energy drops, but the kinetic energy goes up, which correlates with the wave function. Now, the wave function here is only the positive contributing portion of the wave function, but it's exactly the same. So the potential energy goes up, the frequency goes up. I'm sorry, other way. Kinetic energy goes up, the frequency goes up. Now let's finish up with the uncertainty principle. What is uncertainty principle? Basically, what it is that we cannot know the momentum and the position of a particle at the same time. Why? Why is this so? Let's examine it a little further. So if we take a wave function such that it is defined in a very particular location and it's zero everywhere else, that will pinpoint the exact location of a particle on this axis, right? But it loses any information, we lose any information about its state, because now we have a wave function that basically extends to infinity. It has there is no dx there in that function. So there is nothing we can say about, well, shall we say, the momentum of this particle. It's fixed. So in order to construct such a precise wave function, we need to take each individual harmonic functions that represent that particle. Obviously, there isn't a single function, right, for a particle. It has many different quantum states. It has many different wave functions. But the point here is that we need to basically take all of the wave functions that describe a particle to be able to form this singular wave function that pinpoints the particle in its exact location. Now that requires an infinite number of harmonic wave functions to be added together, which is also impossible. So let's finish up with the following equation and introduce the Heisenberg uncertainty principle, which is basically this. So what does this mean? Let's chop this down. We have change in linear momentum. It would be the change in a linear momentum along an axis q, and This right here is the measure, the expression of uncertainty. Now let's do as an example, and let's finish with this. Let's just say that well, actually, let's open up a new page. So here we have the Heisenberg's uncertainty principle, in which we have the uncertainty in a linear momentum and an uncertainty in a position. Okay, so if you look at it closely, if let's say the position is certain, let's say our delta Q is 0, then this can only happen when our delta P is infinite. Okay, think of it as limits, and vice versa. It's also accurate, right? If we know our momentum, our position is it has to be undefined. It cannot be defined. So let's, and yes, this applies to quantum physics, but let's it does apply to everything else also. It's just these uncertainties are so small that are disregarded. So, but let's try an example. This is a good example, and then we'll finish with that. So here is an example of using the uncertainty principle. Let's suppose we have a projectile that has a mass of 1 gram, and we have its speed known to 1 micron per second accuracy. And the point here is to calculate the uncertainty in its position. So we need to estimate the delta P from the Heisenberg's uncertainty principle. Okay, and we have to determine delta P from m delta V, in which delta V is our uncertainty in speed. Okay, so what do? We have our delta Q, which is the uncertainty in the position, equals h divided by 2 m delta V, and m delta V is our impulse, change in impulse, right? So it basically equals to times 10 to the minus 34 joules, sorry. And divided that by 2 times, we have 1 times 10 to the negative 3 kilograms times 10 to the minus 6 meters per second, which gives us uncertainty of 5 times 10 to the minus 26 meters. And this is why in classical mechanics we disregard these uncertainties, because for crying out loud, 5 times 10 to the minus 26. And I don't think we have any instruments that can actually measure that degree of error altogether. So there we go. With this we will finish our chapter 7, and we will get to actually applied stuff, which are actually a lot more interesting. Thank you.